Command line fun. In this module, we'll take an introductory look at a few popular Linux command line programs. Please refer to the Kali Linux training site for a refresher or more in-depth discussion. The Bash environment. Bash is a shell that allows us to run complex commands and perform different tasks from a terminal window. It incorporates useful features from both the Korn shell and C shell. Environment variables. When opening a terminal window, a new Bash process, which has its own environment variables, is initialized. These variables are a form of global storage for various settings inherited by any applications that are run during that terminal session. One of the most commonly referenced environment variables is path, which is a colon-separated list of directory paths that Bash will search through whenever a command is run without a full path. We can view the contents of a given environment variable with the echo command, followed by the $ character and an environment variable name. For example, let's examine the contents of the path environment variable. Some other useful environment variables include user, pwd, and home, which hold the values of the current terminal user's username, present working directory, and home directory, respectively. We can define an environment variable with the export command. For example, if we are scanning a target and don't want to type in the system's IP address repeatedly, we can quickly assign it an environment variable and use that instead. The export command makes the variable accessible to any sub-processes we might spawn from our current Bash instance. If we set an environment variable without export, it will only be available in the current shell. Let's launch another instance of Bash and try to display the variable again. Since we defined our variable without the export command, we can't access it in the new Bash instance. After exiting back to our original Bash session, we have access to the variable again. Now, let's see what happens when we use export to define a variable. Nothing has changed so far, but let's see what happens when we launch a new Bash instance. This time, we can access the variable from the new instance. There are many other environment variables defined by default in Kali Linux. We can view these by running env at the command line. Take some time to review and experiment with predefined environment variables. Tab completion. The Bash shell autocomplete function allows us to complete file names and directory paths with the tab key. This is such a time saver that makes other shells, which lack this feature, feel clumsy and slow. Let's take a look at how this works from the Kali user home directory. We'll start by typing the following command. When we hit the tab key the first time after D, Bash suggests that there are 3 directories starting with that letter, then presents our partially completed command for us. Since we decide to specify desktop, we'll type E followed by the tab key again. At this point, the Bash shell magically autocompletes the rest of the word desktop, as this is the only choice that starts with DE. Refer to your lab guide for more information. Bash history tricks. When engaged in a penetration test, it's important to keep a record of commands that have been entered into the shell. Fortunately, Bash maintains a record of commands that have been entered, which can be displayed with the history command. Rather than retyping a long command from our history, we can make use of the history expansion facility. For example, each entry in our history is preceded by a line number. To rerun a command, we simply type an exclamation mark followed by the line number. In this case, we'll re-execute the command clear, which is identified by line number 32. Another helpful history shortcut is the double exclamation mark, which repeats the last command that was executed during our terminal session. By default, the command history is saved to the bash history file in the user's home directory. Two environment variables control the history size: hist size and hist file size. Hist size controls the number of commands stored in memory for the current session, and hist file size configures how many commands are kept in the history file. These variables can be edited according to our needs and saved to the bash configuration file .bashrc that we will explore later. One of the simplest ways to explore the bash history is right from the command line prompt. We can browse through the history with some useful keyboard shortcuts, with the two most common being the up arrow and down arrow. The up arrow scrolls backwards in history, and the down arrow scrolls forward. Last but not least, holding down Control and pressing R will invoke the reverse I search facility. If we type a letter, for example C, we'll get a match for the most recent command in our history that contains the letter C. We can keep trying to narrow down our match, and when we find the desired command, we'll press Enter to execute it. Bash has a number of history features that can save a great deal of time and repetitive typing. Piping and redirection. Every program run from the command line has 3 data streams connected to it that serve as communication channels with the external environment. These streams are defined as standard input, which is data fed into the program, standard output, which is output from the program and defaults to the terminal, and standard error, which contains error messages and are also displayed by default in the terminal. Piping using the pipe operator and redirection using the left and right angle bracket operators, also known as chevrons or greater than and less than signs, connect these streams between programs and files to accommodate a near infinite number of possible use cases. Redirecting to a new file. In the previous command examples, the output was printed to the screen. This is convenient most of the time, but we can use the right angle bracket operator to save the output to a file to keep it for future reference or manipulation. If we redirect the output to a non-existent file, the file will be created automatically. However, if we save the output to a file that already exists, that file's content will be replaced. Be very careful with redirection. There is no undo function. Redirecting to an existing file. To append additional data to an existing file, as opposed to overwriting the file, use the double right angle bracket operator. Once again, be sure to exercise caution with redirections so you don't overwrite anything important. Redirecting from a file. As you may have guessed, we can use the left angle bracket operator to send data the other way. In this example, we'll redirect the WC command's standard input with data originating from the file we generated in the previous section. Let's try this with WC-M, which counts characters in the file. Note that this effectively connected the contents of our file to the standard input of the WC-M command. Redirecting standard error. According to the POSIX specification, the file descriptors for standard input, standard output, and standard error are defined as 0, 1, and 2, respectively. These numbers are important as they can be used to manipulate the corresponding data streams from the command line while executing or joining different commands together. To get a better grasp of how the file descriptor numbers work, consider this example, which redirects the standard error. Note that error.txt only contains the error message generated on standard error. We did this by prepending the stream number to the right angle bracket operator, where 2 corresponds to standard error. Piping. Continuing with the example using the WC command, let's have a look at how to redirect the output from one command into the input of another. We'll use the pipe character to redirect the output of the cat command to the input of the WC command. This concept may seem trivial, but piping together different commands is a powerful way to manipulate all sorts of data. Text searching and manipulation. In this section, we'll gain efficiency with file and text handling by introducing a few commands: grep, sed, cut, and awk. Advanced usage of some of these tools requires a good understanding of how regular expressions work. Grep. In a nutshell, grep searches text files for the occurrence of a given regular expression and outputs any line containing a match to standard output, which is usually the terminal screen. Consider the following example. We listed all the files in the user bin directory with ls and piped the output into the grep command, which searches for any line containing the string zip. Some of the most commonly used switches include -r for recursive searching and -i to ignore the case of the text. Refer to the grep man page for more information about various options. Understanding the grep tool and when to use it can prove incredibly useful. Sed. Sed is a powerful stream editor. It's also very complex, so we'll only briefly scratch the surface here. At a high level, sed performs text editing on a stream of text, either a set of specific files or standard output. Let's look at an example. We created a stream of text using the echo command and then piped it to sed in order to replace the word hard with harder. Note that by default, the output of the entire command has been automatically redirected to standard output, or the terminal screen. Cut. The cut command is simple, but often comes in quite handy. Cut is used to extract a section of text from a line and output it to standard output. Some of the most commonly used switches include -f for the field number we are cutting and -d to define the field delimiter. Here, we echoed a line of text and piped it to the cut command to extract the second field using a comma as a field delimiter. The same command can be used to cut lines found in text files. This time, a list of users is extracted from Etsy password by using a colon as a delimiter and retrieving the first field. Awk. Awk is a programming language designed for text processing and is typically used as a data extraction and reporting tool. It is also extremely powerful and can be quite complex, so again, we will only scratch the surface here. A commonly used switch with awk is -F, which is the field separator, and the print command, which outputs the result text. Here, we echoed a line and piped it to awk to extract the first and third fields using a double colon as a field separator. The most prominent difference between the cut and awk examples we used is that cut can only accept a single character as a field delimiter, while awk is much more flexible. As a general rule of thumb, use a single awk command instead of multiple cut operations. Practical example. Let's take a look at a practical example that ties together many of the commands we've explored so far. We've been given an Apache HTTP server log that contains evidence of an attack. Our task is to use bash commands to inspect the file and discover various pieces of information, such as who the attackers were and what exactly happened on the server. First, we'll use the head and WC commands to take a quick peek at the log file in order to understand its structure. The head command displays the first 10 lines in a file, and the WC command, along with the -L option, displays a total number of lines in the file. Notice that the log file is text-based and contains different space-delimited fields like IP address, timestamp, HTTP request, etc. This is a perfectly grep-friendly file and will work well for all the tools we've covered so far. We'll begin by searching through the HTTP requests made to the server for all the IP addresses recorded in this log file. To do this, we'll cat the log file and pipe the output into the cut and sort commands. This might give us a clue about the number of potential attackers we're dealing with. Here we see that less than 10 IP addresses were recorded in the log file, although this still doesn't tell us anything about the attackers. Next, we'll use unique and sort to show unique lines, further refine our output, and sort the data by the number of times each IP address accessed the server. The -C option of unique will prefix the output line with the number of occurrences. A few IP addresses stand out, but we'll focus on the address that has the highest access frequency first. To filter out the suspicious IP address and display and count the resources that were being requested by that IP, we can use the following sequence. From this output, it seems that the IP address was accessing the admin directory exclusively. Let's inspect this further. Apparently, the suspicious IP has been involved in an HTTP brute force attempt against the web server. We can verify this with grep's -V flag to reverse the search and only show lines that do not contain the word admin. As we can see, our log files contain no such entry. Furthermore, after about 1,000 attempts, it seems like the brute force attempt succeeded, as indicated by the HTTP 200 message. This is a good example that ties together many of the basic commands we've explored. Editing files from the command line. Next, let's take a look at file editing in a command shell environment. This is an extremely important Linux skill, especially if you happen to get access to a Unix-like OS during a penetration test. Although there are text editors like gedit and LeafPad that might be more visually appealing due to their graphic user interface, we will focus on text-based terminal editors, which emphasize both speed and versatility. Everyone seems to have a preference when it comes to text editors, but we will cover basic usage for the two most common options, Nano and VI. Nano. Nano is one of the simplest to use text editors. To open a file and begin editing, simply run Nano, passing a file name as an optional argument. Once the file is opened, we can immediately start making any required changes to the file, just as we would in a graphical editor. The Nano command menu is located at the bottom of the screen. Some of the most used commands to memorize include Ctrl-O to write changes to the file, Ctrl-K to cut the current line, and Ctrl-U to uncut a line and paste it at the cursor location. Ctrl-W is used to search within the file, and finally, Ctrl-X is used to exit. For additional information regarding Nano, refer to its online documentation. VI. VI is an extremely powerful text editor, capable of blazing speed, especially when it comes to automating repetitive tasks. However, it has a relatively steep learning curve and is nowhere near as simple to use as Nano. Due to its complexity, we will only cover the very basics here. As with Nano, to edit a file, simply pass its name as an argument to VI. Once the file is opened, enable Insert Text Mode to begin typing. To do this, press the I key and start typing away. To disable Insert Text Mode and go back to Command Mode, press the Escape key. While in command mode, use DD to delete the current line. Press YY to copy the current line, and press P to paste the clipboard contents. To delete the current character under the cursor, press the X key. To write the current file to disk and remain in VI, type :W. Type :Q followed by an exclamation mark to quit without writing the file to the disk. To quickly save the file and quit VI, enter :WQ exclamation point. Because VI seems so awkward to use, many users avoid it. However, from a penetration tester's point of view, VI can save a great deal of time in the hands of an experienced user and is installed on every POSIX compliant system. Comparing files. File comparison may seem irrelevant, but system administrators, network engineers, penetration testers, IT support technicians, and many other technically oriented professionals rely on this skill fairly often. In this section, we'll take a look at a couple of tools that can help streamline the often tedious but rewarding process of file comparison. COM. The COM command compares two text files, displaying the lines that are unique to each one, as well as the lines they have in common. In the first example, COM displayed the unique lines in scan-a.txt, the unique lines in scan-b.txt, and the lines found in both files respectively. COM outputs 3 space offset columns. The first contains lines that are unique to the first file or argument. The second contains lines that are unique to the second file or argument. And the third column contains lines that are shared by both files. The -N switch, where N is either 1, 2, or 3, can be used to suppress one or more columns depending on the need. Let's take a look at an example. This time, COM displayed only the lines that were found in both files since we suppressed columns 1 and 2. Diff. The diff command is used to detect differences between files, similar to the COM command. However, diff is much more complex and supports many output formats. Two of the most popular formats include the context format and the unified format. To display results in context format, use the -C option. This output uses the dash indicator to show that the line appears in the first file but not in the second. Conversely, the plus indicator shows that the line appears in the second file but not in the first. Now, let's see what the unified format returns. The most notable difference between these formats is that the unified format does not show lines that match between files, making the results shorter. The indicators, however, have identical meaning in both formats. Vim Diff. Vim Diff opens Vim, an extended version of VI, with multiple files, one in each window. The differences between the files are highlighted, which makes it easier to visually inspect them. There are a few shortcuts that might be useful. For example, pressing Ctrl-W followed by an arrow key allows us to switch between windows. Pressing the right bracket and the letter C will jump to the next change in the diff. And the left bracket followed by the letter C will jump to the previous change. The DO key combination will get a change from the other window and put it in the current one. The DP combination will put the change from the current window into the other one. To quit Vim Diff, use the same shortcuts as VI. Managing processes. The Linux kernel manages multitasking through the use of processes. The kernel maintains information about each process to help keep things organized, and each process is assigned a number called a process ID. The Linux shell also introduces the concept of jobs to ease our workflow during a terminal session. For example, this is a pipeline of two processes, which the shell considers a single job. Job control refers to the ability to selectively suspend the execution of jobs and resume their execution at a later time. We can achieve this with the help of specific commands, which we'll soon explore. Backgrounding processes. The previous jobs in this module have been run in the foreground, which means the terminal is occupied and no other commands can be executed until the current one finishes. Since most of our examples have been short and sweet, this hasn't caused a problem. We will, however, be running longer and more complex commands in later modules, which we can send to the background in order to regain control of the terminal and execute additional commands. The quickest way to background a process is to append an ampersand to the end of the command to send it to the background immediately after it starts. Let's try a brief example. We'll send 400 ICMP echo requests to the local interface with the ping command and write the results to a file. The execution automatically runs in the background, leaving the shell free for additional operations. But what would have happened if we had forgotten to append the ampersand at the end of the command? This command will run in the foreground, and we are forced to either cancel the command with Control-C or wait until the command finishes to regain control of the terminal. The other option is to suspend the job using Control-Z after it's already started. Once a job has been suspended, we can resume it in the background using the BG command. The job is now running in the background, and we can continue using the terminal as we wish. While doing this, keep in mind that some processes are time sensitive and may give incorrect results if left suspended for too long. For instance, in the ping example, the echo reply may come back, but if the process is suspended when the packet comes in, the process may miss it, leading to incorrect output. Always consider the context of what the commands you are running are doing when engaging in job control. Jobs control, jobs, and FG. To quickly check on the status of our ICMP echo requests, we need to make use of two additional commands, jobs and FG. Let's begin by starting and suspending two long-running commands. The built-in jobs utility lists the jobs that are running in the current terminal session. Running the FG command, followed by a % and job number, returns a job to the foreground. We'll use Control-C to terminate this ping process and run jobs again. With only one job running, we can run FG without any additional arguments to return it to the foreground. Specific jobs can also be referenced by their process ID number or command name. Process control, PS and kill. One of the most useful commands for monitoring processes on almost any Unix-like operating system is PS, which is short for process status. Unlike the jobs command, PS lists processes system-wide, not only for the current terminal session. PS is considered a standard on Unix-like OSs, and its name is so well recognized that even on Windows PowerShell, PS is a predefined command alias for the get process commandlet, which essentially serves the same purpose. As a penetration tester, one of the first things to check after obtaining remote access to a system is the software currently running on the compromised machine. This could provide clues to help elevate our privileges or collect additional information in order to acquire further access into the network. As an example, let's start the LeafPad text editor. Now, let's try to find the LeafPad process ID from the command line using the ps command. We'll run ps with the -ef options, where E selects all processes and F displays a full format listing. Finding our LeafPad application in that massive listing is definitely not easy, but since we know the application name we're looking for, we can replace the -E switch with $C and specify the command name, which is LeafPad in our case. The process search has returned a single result which contains LeafPad's process ID. Take some time to explore the PS manual, as it really is the Swiss Army knife of process management. Let's say we now want to stop the LeafPad process without interacting with the GUI. The kill command can help us here, as its purpose is to send a specific signal to a process. The kill command requires the PID of the process we want to send the signal to. Since we've already gathered LeafPad's process ID, we can proceed. Because the default signal for kill is SIG_term, or request termination, our application has been terminated. We can verify this with PS after killing LeafPad. File and command monitoring. It's extremely valuable to know how to monitor files and commands in real time during the course of a penetration test. Two commands that help with this task include tail and watch. Tail. The most common use of tail is to monitor log file entries as they are being written. For example, we may want to monitor the Apache logs to see if a web server is being contacted by a given client we are attempting to attack with a client-side exploit. The -F option is very useful. It continuously updates the output as the target file grows. Since our local Apache web server is already running, we'll visit the default page using Firefox. If we go back to our terminal, we should see the requests made in the log file. Another convenient switch is -NX, which outputs the last X number of lines instead of the default value of 10. Tail has a number of other useful options outlined in its man page. Watch. The watch command is used to run a designated command at regular intervals. By default, it runs every 2 seconds, but we can specify a different interval by using the -NX option to have it run every X number of seconds. For example, this command will list logged-in users, output from the W command, once every 5 seconds. To terminate the watch command and return to the interactive terminal, use Ctrl+C. Downloading files. Next, let's take a look at some tools that can download files to a Linux system from the command line. wget. The wget command, which we use extensively, downloads files using the HTTP and FTP protocols. wget can be used along with the -O switch to save the destination file with a different name on the local machine. wget has many features and can do far more than simply download files. Refer to its documentation for more information. curl. Curl is a tool used to transfer data to or from a server using a host of protocols. A penetration tester can use curl to download or upload files and build complex requests. Its most basic use is very similar to wget, but with a lowercase o to specify the output file name. Curl is incredibly versatile, and you'll find ample documentation and example usage online. Axel. Axel is a download accelerator that transfers a file from an FTP or HTTP server through multiple connections. This tool has a vast array of features, but the most common option is -n, which is used to specify the number of multiple connections to use. We also like using the -a option for a more concise progress indicator and -o to specify a different file name for the downloaded file. Axel speeds up downloads extremely well and is especially useful for large downloads. Customizing the Bash environment. Bash history customization. Earlier in this module, we discussed environment variables and the history command. We can use a number of environment variables to change how the history command operates and returns data. The most common include hist_control, hist_ignore, and hist_time_format. The hist_control variable defines whether or not to remove duplicate commands, commands that begin with spaces from the history, or both. By default, both are removed, but you may find it more useful to only omit duplicate commands. The hist_ignore variable is particularly useful for filtering out basic commands that are run frequently, such as ls, exit, history, bg, etc. Let's run a few commands to see if history ignores our specified commands. As expected, the ls and history commands do not appear in our command history. Lastly, hist_time_format controls date and/or timestamps in the output of the history command. In this example, we used %F, or year, month, day, ISO 8601 format, and %T, 24-hour time. Other formats can be found in the strftime man page. Alias. An alias is a string we can define that replaces a command name. Aliases are useful for replacing commonly used commands and switches with a shorter command or alias that we define. In other words, an alias is a command that we define ourselves, built from other commands. For example, we typically tend to use ls-la to display results in a long list, including hidden files. Let's take a look at how we can use an alias to replace this command. By defining our own command, lsa, we can quickly execute ls-la without having to type any arguments at all. We can see the list of defined aliases by running alias without arguments. Persistent Bash customization. The behavior of interactive shells in Bash is determined by the system-wide bashrc file located in /etc/bash.bashrc. The system-wide bash settings can be overridden by editing the .bashrc file located in any user's home directory. In the previous section, we explored the alias command, which sets an alias for the current terminal session. We can also insert this command into the .bashrc file in a user's home directory to set a persistent alias. The .bashrc script is executed anytime that user logs in. Since this file is a shell script, we can insert any command that could be executed from the command prompt. Let's examine a few lines of our default .bashrc file. You might recognize the hist size and hist file size environment variables, and the alias command that displays colored output. You will also find some other aliases in this file that are commented out. Wrapping up. In this module, we took an introductory look at a few popular Linux command line programs. Remember to refer to the Kali Linux training site. For a refresher, or more in-depth discussion.